I started my own manufacturing business and been producing sportswear for cricket, football, rugby, this sort of thing. And incidentally, I am the past chairman of the Textile Institute. That's enough about myself. On my left, we've got Dr. Seshadri Ramkumar from Texas Tech University. He's going to speak to us on development of smart textiles using novel non-woven technology. Then to his left is Mr. Sati Thakon, who's going to read a paper written by Mr. Pichai Uttam, both of them from United Textile Mills Company Limited, Thailand, on development of a color matching support system in bleaching and dyeing. I was going to say, if all the four speakers are over here, I was going to request them to please keep to 20 minutes each, and rather 15 minutes than 32 minutes, because they'll only be robbing time from the speaker following them. And it would be most unfair on the last speaker who wouldn't have enough time to do full justice to all the hard work he's done in preparing this paper. Anyway, it looks as though we have a whole rest of the first half of the afternoon for just the two speakers. Mayor, would you like me, Mr. Ramkumar, to go first? Well, in that case, you just say whatever you can do, okay? Whatever comes to you, not to disappoint the people. May I ask you to that, please, President? You can overrun now if you wish.
Sure, I will try to be.
Not too long.
Yeah. And at the outset, I would like to thank the Textile Institute, Egypt section, and the organizing committee for giving me an opportunity, and my good friend and mentor, Mr. Krishan Vigani, for being so patient and being chairing this session. And I am Ramkumar. I live in the States, and they shortened my name to Ram. So I work for Texas Tech University. It's a state university in the state of Texas. And I hold a primary research position in the Textile Research Center. My voice is audible.
You better stop.
And I hold a primary research position in the government lab. It's a state lab at Texas Tech University, and it's known as International Textile Center. And I also hold adjunct professor positions in 3 departments: Department of Chemical Engineering, Plant and Soil Science, and Environmental Toxicology, where I direct master's and the Ph.D. thesis program, and I am the major advisor for 5 graduate students so far. And I graduated from Leeds University, and I moved to the other side of the Atlantic in 1999. And I will talk this afternoon about a new initiative which came to me as a luck. This was a kind of a Department of Defense supported huge program. It's a kind of a consortium of 3 universities: Universities of Texas, University of South Florida in Tampa, and Texas Tech University. They pooled certain brains and then formed a consortium to work on protective clothing, not only protective clothing substrates, but also countermeasure substrates to chemical and biological warfare. This program started in 2000, and it was quite fortuitous to have this program running even before the September 11th incident. And after September 11th incident, this program got real boost, and there has been steady flow of money coming in and a lot of political support within the USA, and the whole program is under this group known as Admiral Zumwalt National Program, and Admiral Zumwalt was the Commander-in-Chief for Vietnam War, and because of his support, Texas Tech University got into the program. And I serve as a principal investigator, and for more than 2 years, and I've been fortunate enough to receive nearly $1 million grant to set up a nonwovens lab that will develop protective clothing substrates, and phase 1 research will concentrate on developing chemical absorbent substrates that will tackle toxic chemicals such as sarin and nerve gas. And so far I have been able to establish a nonwoven facility, and the lab is up and running since July. And this is the goal. It has only one goal. The primary goal is to develop lightweight chemical warfare protective substrates, which should impart the necessary protection and comfort. See, why should I go for non-woven substrates when there are other substrates available? If you want to tackle nuclear substance, you can have a lead hood, and that would tackle all the hazards due to nuclear threats. But the problem is weight as well as comfort, and those structures such as Teflon or any other Gore-Tex components that are available in market will not impart the necessary comfort. So we thought of developing lightweight composite substrates using nonwoven technology. Having given the prelude on my program, and these are the technologies that are involved. This morning in a plenary talk, Dr. Nancy Castle spoke about nanotechnology. And as far as textile is concerned, the nonwovens technology is burgeoning. This is the one which is having a lot of prominence, and a lot of developments are coming in this area, nonwovens technology. Again, nanotechnology is an emerging field of science. Nano means it's 1 billionth of a meter. You are understanding the properties and characteristics of material in a minute scale. And then membrane technology. Membranes are used as protective substrates, and all pesticide protection components are made of membrane. So my program will utilize all these 3 emerging technologies, which are very topical, and there is also a political reason. All these technologies attract a lot of funding so that will keep my lab going. So it's part of survival as well. So what is nonwovens technology? Just a brief introduction about this technology. Nonwoven technology is the advanced method of developing textile substrate. As the name indicates, it bypasses 2 important textile manufacturing operations, the spinning and weaving. The 2 advantages are cost and productivity, apart from certain end-use applications of products you get from nonwoven technology. It saves cost by eliminating conventional processes of spinning and weaving. It should be noted that this is not a process where you could totally wipe out these 2 technologies. These 2 technologies will exist because of certain advantages they have. It's only a kind of technology where you use it to develop certain advanced products. So spinners and weavers should not be worried that this technology will supersede and eliminate the conventional technologies. And so far, this technology has been very useful in developing high-tech and value-added products. And Dr. Siam spoke about the development of apparel products using the nonwovens technology, and things are happening in this arena in North Carolina State University, and I'm not so far having any research program that concentrates on developing apparel substrates using nonwovens technology. And when we talk about nonwovens technology, these are the common technologies that are available in the market. Needle punching technology is the oldest conventional form of nonwovens technology. As the name suggests, the fibers are made into substrates, planar substrates, using needles. So needles are used to punch the fibers to give a coherency, to make it in a form of planar substrate. So that's needle punching technology. And these 2 technologies are synthetic technologies, melt flowing and spun bonding. Each technology has its own niche area. Melt-blown products are good filtration media. Spun-blown products add strength to the melt-blown products. And again, North Carolina State University is pioneering in this area. And thermal bonding technology, as the name suggests, fibers are bonded using heat, either by using compacting rollers or oven. And my lab in May, just after I return to the state, I will be having a state-of-the-art thermal bonding oven, which is part of phase 2 money. And again, if you use air, it becomes air-lay technology, and if you use water, millicules of water flowing at a high rate, the fibers are bonded to form a coherent substrate. It's not hydroentanglement. So these these are some of the common technologies that are available in the market and which are widely used. And my lab has a needle punching technology. You can say what is a big deal to have a needle punching technology. Needle punching technology is old, but there are certain developments that have legislated this technology in the past 5 to 10 years, and my lab is the first and only facility in the US to have the state-of-the-art needle punching technology. I'll show several cartoons that will follow the slide. What is needle punching technology? Loose textile fibers such as polyester, cotton are made into textile fabrics. When we are talking about non-wovens technology, it would be better to characterize these fabrics as substrates, because we still have to prove that these non-woven materials are breakable and could be made into apparel type of fabric. So just to be on caution here, note I use these products which are developed using non-wovens technology as substrates by interlocking them with the help of needles arranged in boards known as needle boards. So as the name itself suggests, we use some kind of needles arranged in certain fashion to make a substrate which has necessary strength and which has certain characteristics that find applications in carpets. Most of these carpets are made by these days by needle punching technology. Most of the HEPA kind of filtration products, air filters, these are all made by needle punching technology and other technologies. So needle punching technology is versatile. The versatility, it can handle different types of fibers. You can blend different types of fibers, which is not possible in the synthetic technologies such as melt blown and spun bonding. It is conventional, it is as old as far as non-woven is concerned, and it can handle a variety of fibers. Because of these two particular reasons, I chose needle punching technology. Because what was my ultimate goal? My ultimate goal is to develop a lightweight composite chemical adsorbent substrate that should give necessary protection. You can impart necessary protection against chemical toxins if you use any kind of charcoal, any kind of activated carbon. But we cannot touch activated carbon because it is not comfortable. There are a lot of health hazards involved. But how can I enhance the comfort of those adsorbent products? Either you have to use a fiber which is very near and dear to the human skin. What are the fibers which are near and dear to the human skin? First comes cotton, next comes polyester. So other technologies will not be able to handle this kind of mixture. And this is because of the primary reason I chose non-wovens technology. So I have given an idea, why did I go for this? And okay, non-wovens technology, when we talk about non-wovens technology, needle punching is over. So why do you go and work on an area which is kind of saturated? What is the need for you to go back again? One, for the particular end use, for the application I am focusing, needle punching is suitable. Okay, having said that, should I go for an existing or very old conventional needle punching technology? I should not. I should go for something which is emerging so that I could do a lot of fundamental studies. Because I'm being an academic, I should substantiate my research with some kind of fundamental study. So I looked into the literature, I looked into the trade and what is happening here, and two things have been taking place. Again, needle punching is a European technology. There are two prominent leaders in this technology. One is German, that's Dilo. Another one is Austrian, it's Fibre. So these two people are working, are very competitive, and they are developing a lot of new type of needle punching. There's not much of tremendous development, there's not much leap in the technology here, but there are a little bit here and there ramifications, and these ramifications have led to a lot of patents. And I chose Fibre because of this particular characteristics. Why? What is happening in the development? As far as development in case of needle punching, there is enhancement in efficiency of needle punching. This is basically commercial perspective. So the Fibre machinery that is in Linz, Austria, has come up with the technology known as H1 technology. The name doesn't mean anything, it's just a name given by the company. And they claim that particular needle technology has increased efficiency. I'll tell you why. And then the quality of the non-woven substrates developed using that particular H1 technology are superior than the conventional technology. This is the manufacturer's claim, and I'm still collecting data on this. And what my lab has is H1 technology, and I'm again fortunate. TTU stands for Texas Tech University. Is the first and only facility in the US to have this H1 technology needleloom, and that is of manufacturing scale. It is 1.3 meters with full-fledged non-woven facility, and I will show you the installation process in a minute. So that again gave me a leap that I was instrumental in establishing establishing a new facility at Texas Tech University, because at Texas Tech University we did not have any nonwovens program at all. And the needle loom has to be fed by a full feeder unit, and this is more or less a woolen feeding system, and that is from William Taylor Machinery in England. And the needle loom is branded as H1 technology from Fibre Machinery Austria. So I was able to put these two companies together and come up with an installation program, and the total cost, it's a brand new machinery, was around $450,000 US. It's a lot of investment, and I was lucky enough. Maybe I became an early bloomer here, because in academia it is very difficult to get this kind of money in 2 years, and I was lucky enough, maybe what's the reason I do not know. So this is the thing that has happened, and this is how the machinery looks. So we talked about needle loom, and you can see the needles. So what happens? The fibers, we are all familiar with fibers. These fibers are fed, and there is a feeding unit. I will show you in a minute the whole cartoon of the feeding unit. The fibers are fed using the feeding unit, which is from England, William Tatum Rochdale in Manchester. And these fibers pass through an underplate or a bed, and the needle board, the needles, you see a lot of needles, there are around 3,600 needles. In my 1.2 meters width, the number of needles is 3,600. These 3,600 are arranged in a regular fashion on a contour platform. This is what H1 technology has. The H1 technology has a contour needle board. You see, in conventional needle loom, these needles are arranged on a flat bed, whereas this particular technology has the needle arranged in a specific contour which enhances the efficiency. So that is a patented invention from Fibre. Ernst Fibre is a pioneer, epitome of machinery, textile machinery. He passed away last year. So these loose fibers are passed through the flat bed, and these needles go up and down. It's kind of punching. As the needles punch on the fibers which are fed on a regular fashion, you get a coherent mat, and this is what H1 technology does. And in the US, my lab is the first and only facility, so I'm again lucky. It's kind of self-serving, but I'm really very proud of this kind of accomplishment. So this is a full-blown image of the needle loom, where you can see the needles arranged in a contour fashion. Again, when you see these, the orifice through which the fibers are fed, you see that there is a contour here. And this kind of contour is scientifically known as oblique angle penetration. If you are a scientist or technocrat, if you want to know what kind of penetration you are seeing, this is known as oblique angle penetration. What happens when the fibers come into the needle loom? They are in loose form, they are bulky, they are fluffy. So you need more room for the fibers to pass through. And halfway through, when these fibers pass through to 50% of the needle punching, already they are condensed. So what happens? You don't have to have the same depth. So what is happening? When it comes halfway through, the depth decreases. So the amount of needle penetration decreases. That saves the cost. So it's manufacturing for wise, it increases the efficiency. So that's what it is claimed. So that's a neat idea. It was not my invention, it was Dr. Ernst Fibre invention. So this is the beauty. This is the added advantage of this system. So having explained that these are two specific features of this H1 technology, it has a contoured needle zone. When you go back to the previous slide, you see it's not a flat needle zone, it is a contour or arcadian. In scientific term, anything which is not flat, you can say it has some specific shape, and a good term to use is a contour. So it has a contour needle zone, and when it comes, when the fibers come, the needle come from this part, go down all this, so you have a longer penetration. So the longer penetration takes place only in the initial phase where you need that much penetration. So you are saving the cost, you are not breaking the substrate. That's the reason the quality enhancement. You see, we don't have much leap in the technology, but there are ramifications which benefit the output, which benefit the product. So having substantiated the claims that this technology increases the efficiency, this technology produces substrate which has superior quality. Now go on to the results. So these two, I have substantiated these with some diagrams, and this is how the patterns are formed. So this is a side view. actually the machine runs. You see the fibers, loose fibers, these are fed by the feeding rollers. The needles are running in the console. You can see the fibers. I told you that these fibers are bulky and fluffy, so the fibers pass through. And when it comes in the halfway, this is a 50% way, the depth of penetration decreases and you see the substrates form. This is a spin photography of the development of substrates. So this is a neat technology. And there is no meaning to this. This is just a company brand, and this has been carried along, and my lab is the only one. And I understand that there are in total globally 22 such installations, and my width, you see the width is, this is the side view, so the width from here to here is 1.2 meters, which is having a manufacturing scale level. So what are the features? So having explained the technology, what are the features? There are good, these substrates have good arrangement of fibers, because I told what I have alluded to is that the breakage in the fibers is very minimal because of the way the fibers are punched. So what do you expect? You expect good fiber orientation and good fiber entanglement, and because of pure penetration in the second phase of needle punching, the substrates are strong. So these are some technological advantage, and this is how the machine goes. So this is 1.2 meters width. You see the needle bed, this is how the needle. So you can fit the needle board here. You can just slip the needle board through this board. So this is the side view. This is the picture taken when the machine is being assembled. So this is the whole rugged, solid structure of parent. See the branding here of parent, and this is how the patterns come out, or substrates come out, and the needle board can be slipped in. It's very quick. So this cartoon shows the needle blue. And this is how the feed unit looks. So I'm indeed glad, because I had alluded that it is a full manufacturing scale facility. This is a feeder unit alone. So this is a typical woolen or worsted feeding unit. The fibers are fed in the upper feeder. Then you have a double cylinder car, and the maximum speed I go is 750 revolutions per minute. So the fibers are open, similar to short staple or long staple, where you tear the fibers to get more uniform feed. And this is a unique feature of a needleloom. This is known as a cross-laker, which arranges, which randomizes the fiber in a uniform way, so that your feed material to the needleloom is uniform. So a feed unit in a regular or a conventional non-woven operation consists of a hopper feeder, a double cylinder cart, and a cross-laker. Again, this cross-laker is a patented invention way back 50 years ago by William Tatum. It's a small family-owned company in Rochdale, England. So this is feed unit. And this is how the arrangement looks. You see, this is a cross-laker. It's an L-shaped arrangement. So the hopper feeder starts here, then you have a car, then you have a cross-laker. This cross-laker feeds the needleloom, and the entire thing is operated by a single console here, and the fabrics are collected to the taper. So this is a neat installation. And this is how the operation starts. This is the hopper feeder. It's just like a regular hopper feeder in any short staple loom. The fibers are fed. The minimum amount of fiber I need is 25 pounds or 10 to 15 kilos. These fibers are then carried over by the conveyor belt here, and then these are then carded. So carding is a process where you individualize the fiber. We are all familiar with short staple carding. The process is similar. Then these carded fibers pass through the cross-laker, and then you have a parallel loom here, and you develop a needle punch substrate. So on March 18th, we had a patent application to be filed where we developed the unique chemical adsorbent substrates, and hopefully the patent would be approved. So far the program is very good, and this is how the fabrics are developed. You see the cross-laker brings out the substrates like this, which are not coherent, which are not consolidated. Then these cross-layer substrate or cross-layer web pass through the needle board, and this gets punched, and you have the fabrics here. And the speed here is 20 to 25 yards per minute, very high production. And if you talk about in terms of penetration, the maximum speed is 1300 strokes per minute. On an optimum level, I run the machine at 850 strokes per minute, and this technology will allow the fibers to be punched at 1300 strokes per minute, and the yardage is 20 to 25 yards. And this is the technology, this is the line I have, hopper feeder, double cylinder card. The maximum speed I could go is 760 revolutions per minute. Translator and H1 technology needleloom. That is just an outline of the operation. And certain products I developed to find applications in automotive textile, composite and hybrid products. And this is where my absorbent products fit in, because it is not a single layer, it's a composite layer, where inner layer is a chemical absorbent layer. The next to skin layer is a comfort layer or pre-filtration layer, and I was also able to develop paper cells, industrial pipes, filters, and mining tools. A kind of a myriad of applications you could develop. And what are the capabilities? The capabilities of the needleloom is very versatile, the versatility. And handle both fiber, synthetic, and natural. So this is the strength. The maximum stroke is 1300, and the uniformity of the product is very good, because I have it similar to an auto level a draw frame. We have a system known as microfeed unit that is just after the auger feeder and the feed roller to the card, which feeds uniform material to the card. And this is the setup of the feed unit. It has auger feeder as well as blender. It blends and feeds. Then the uniformity of the material that is fed to the card is maintained using this auto leveler feed. Then I have 10 cylinder card. The carding action takes place between worker and stripper, similar to the woolen card. And in total there are 10 carding zones with 2 big carding drums. That's the translator. So all these cartoons have been shown, and my card is capable of running anywhere from 1 denier to 6 denier and 1.5 to 3 inches length of the fiber. So I can handle wool, I can handle mohair, and I can handle alpaca. And it is also capable of handling cotton and wool, and so far I've been successfully developing wool up to 54 microns, and I need a brush. I'll show you some results on initial trial. And the lab was set up only on July 28th. Saturday, so I've been successful in developing a lot of fabrics. I had blended the fabrics, developed cotton, lyocell wool, polyester, nylon. You see 6 linear 3-inch maximum in the operate, Kevlar, and then as well chemical absorbent substrates. And again, I was able to I manipulate the weights, because achieving this proper weight is very important as far as nonwoven substrates are concerned. The minimum weight I could achieve is 22 grams. GSM stands for grams per square meter, 22 grams per square meter, because my ultimate aim is not to get a thick carpet material. My ultimate aim for this program is to develop lightweight thin material, and so far I've been able to successfully needle punch background 1.5 denier 1.5 inch fiber, 20 grams per square meter. And then phase 1 concentrated on using cotton, because Textile is a cotton state and I need to work on cotton. And so far I've been only successful in developing blends of cotton, and I will share some results on Tima cotton. Tima cotton is a extra length cotton, and when I used cotton I needed a separate opening line, which I used a regular short staple line to clean the cotton, to open the cotton, and then to open the cotton from a short staple line was fed to the hopper feeder in my nonwovens line. And this is a typical operation, typical outline of the process I used for cotton. So cotton, extra long cotton, Tima cotton, 20 pounds of the cotton was first beaten through monocylinder, then the dust was extracted, then it was cleaned through ERM. I didn't give any harsh beating. And the opened cotton were processed in the regular nonwovens line. I showed only blends of cotton with, I didn't develop 100% cotton nonwoven substrate. So far I developed 60 cotton, 40 polyester. So this is the characteristic of cotton I use. It's extra length, so 1.3, 86% uniformity, 4, and it's high strength cotton, 43 grams per hex. And 50-50, this ran very successfully, and I was able to achieve wide range of weights, 40 to 80 grams per square meter. And then what properties I tested? Mechanical property. When we talk about nonwovens, there are no standard methodologies, so I'm also establishing standards to understand the bursting strength, because bursting strength is very important when you talk about composites, particularly for nonwoven composites. So I'm standardizing, and one student is working under my supervision on his MS thesis to standardize the quality testing methods, particularly the bursting strength. And this is how the tester looks like, and we are optimizing the setup, because you see nonwovens are not like woven structures, they are very flexible. And in certain cases, when you are talking about 45 to 50 GSM substrates, they will not break, they keep stretching. So we need to optimize, and this is one particular setup we are using. I think what are the ongoing experiments? Currently, we are developing non-woven fabrics at different blend levels, and I am experimenting with short staple cotton, upland cotton. And in May, I will be having another machine, which is thermal bonding machine. So this needle punching technology, this thermal bonding technology will complement the needle punching technology, so I will develop composite substrates, high loss, gradings, and all additional kind of substrates. And this is again a flatbed, it is not a compressing thermal oven. The people in the non-woven state would know it is a throughput, through air non-woven thermal oven. The width is 1.2, this matches exactly with the existing H1 technology needleloom. And this is again from Phoenix, England, and my end use would be the products I would be developing would be these lightweight wearings. Again, I'm just reading the same thing again. My interest is only lightweight, high loss bags and compressed wearings. And this is how the machinery would look like. The needle punch substrate would be passing through the oven. I do apologize for a bad start here because it was taken in the dark in the manufacturing facility. And the thermal oven bonds several layers. It's kind of making a sandwich. You know, we make bread sandwich. So the thermal oven makes the sandwich, and these are collected in the conveyor belt. This is the top view, and this is the side view. This is the burner of the oven, which makes the composite. And again, I come to the conclusion, the research program will effectively utilize needling and thermal bonding capabilities to develop smart and novel substrates. I didn't give you the details on the smart structures, but the smart structures has chemical absorbent capabilities, and since we are filing a patent on it, I was not allowed by the Soldier Biological Chemical Command to talk anything on that, but it uses these two technologies to develop chemical absorbent clothing. And the primary use, I have not done anything on biological or anthrax absorbing substrates. It would be only chemical absorbing structures. And the final conclusion is state-of-the-art H1 technology loop has been installed and it's fully running successfully. And this is used, this has been very successful so far, this technology, to play with different fibers and develop non-woven substrates, which will have a number of applications, including smart and novel ones. And with that, I conclude, and I do appreciate your patience, and I thank again the Textile Institute and Chairman for giving me an opportunity.
Thank you very much. Can we have the lights on, please?
Can I have a question, please?
Yes, sir.
What's the effect of fiber lens and the non-woven?
Yes, it has, because you see, my needle punching technology is based on carding, and only certain fibers can process, so that depends on the card clothing. So that you have to plan. So my carding machine will successfully operate any apparel grade fiber 1 to 3 inches. And I was successful enough, not 100% to card microlinear fibers. I was not successful, but it is possible to run anywhere from 1 to 6 linear fibers.
Speak in please. Nobody knows where the light switch is.
I didn't see who was talking, so I just
Second question, please.
Yes, sir.
What is, if we compare this to woven fabric, what's the variation between thickness variation across material?
It would be bulkier. Non-woven substrates are a bit bulkier. And my interest
I was asking about the variation.
لا عشان بس المترجم.
Would you be kind enough to address your question through the chair, please? That is the right thing to do. Because I wanted to kick off and suddenly the discussion all started off.
I was just asking about thickness variation in comparison to woven material.
Is it would be, at least my understanding is 5% variation is higher than woven substrate.
Higher.
Yes, it's higher. That is obvious as far as non-woven. Maybe I didn't optimize the setting, so
But was it less
it
than
would be a little bit higher than the woven.
Less than 5% or more?
Pardon me, variation would be higher than a woven.
Less than 5% or more?
My experimental data suggests it's 4.5 to 5%.
Thank you.
But to be honest, it is also not logical to compare that way woven and non-woven. But in general, it's higher for that particular weight. Yes, this is only kind of empirical data I have.
Thank you. Can I use my chairman's prerogative and make a comment myself, please? I was very excited at the title of your lecture, particularly the word smart. And I don't mind admitting I was a little bit disappointed. I thought somebody's trying to sell us that non-woven machine. We would have been more interested to know more about the what smart textiles you had in mind,
Yes.
rather than all the details of the machine.
See, I was not allowed to tell.
You
What
said
is
that,
happening is this much I can tell. There are certain polytetrafluoroethylene electrode sensors.
No, please.
Okay. The smart term, yes, this is what my patent does. There are polytetrafluoroethylene sensors which would be sandwiched in these needle punch substrates that would be able to absorb the chemical toxins. So what happens is there is a kind of an electronic component involved. So when there is a kind of sarin, or if you talk about pesticides, there are certain pesticides like parathion and malathion. So I'm not a chemist, so I do not know the chemical constituents. When these pesticides, which are prone to be toxins, come and hit these substrates, the polytetrafluoroethylene electrodes have a different kind of luminance, and the chemical absorbing substrate absorbs them. So it has a multidimensional aspect, and I was not allowed to talk anything about it.
Any more questions to Dr. Ramkumar? No? Thank you very much.
Thank
Please.
you.
Thank you. Thank you. Now, just a second. We had here Mr. Sati Tapong. Disappeared.
I believe he's trying to straighten out the computer
Right,
presentation.
yeah. We nearly did not have any other speaker, but I'm glad at the last minute you made it. We have now had Ms. Uncle and is your colleague here, Dr. Would you like to join us? They're both from North Carolina State University, USA, and Technical University of Istanbul, Turkey. Why is it Istanbul, not Istanbul? Oh, is a printing error. Thank you very much.